Welcome to our tutorial, enabling hardware-software co-design of distributed deep learning training platforms. Essentially here, we're going to be talking about distributed training kind of from a systems perspective and introducing our simulation infrastructure, ASTRA-sim. So this is the set of presenters today. So I'm Tushar Krishna. I'm an associate professor at Georgia Tech. With me are Saeed Rashidi, who's a PhD student at Georgia Tech, William Vaughan, who's also a PhD student at Georgia Tech, and Taekyung Hyo, who's a postdoctoral fellow at Georgia Tech. And we also have Srinivas Sridharan, who will be joining us virtually. He's a research scientist at Meta. And I also want to acknowledge some of our collaborators, Sudarshan Srinivasan from Intel, Tarannum Khan, who's a graduate student with Aditya Kela at UT Austin, and a growing set of collaborators who've been contributing to our tool and infrastructure. So this is the agenda for today. So I will kick things off by giving everybody an overview of distributed deep learning training. Then Srinivas will kind of come in. He will talk about challenges on designing distributed training systems, kind of giving an industry perspective of some of the challenges and just give a glimpse of what Meta has been doing in this space. Then we'll introduce our simulator ASTRA-sim. Saeed will kind of go into those details. Then we'll have a short break for coffee. After that, we kind of go into a hands-on mode. William and Taekyung will kind of go through exercises for using ASTRA-sim. We have a set of demo exercises that we already prepared for this tutorial. And finally, Taekyung will talk about some closing remarks and future developments in this space. So this is the tutorial website. You can also find it through, of course, the MLSys page. This has the source code and the Docker image for what we're going to be talking about. And the tutorial is also being recorded. So we actually plan to release the recording as well after the tutorial. So this is the page I was talking about. So if you go here, we've kind of given you installation instructions to install ASTRA-sim from the source, or you can just get started with a pre-built Docker image. The Wi-Fi here is apparently quite slow. So if you want to go ahead and get started, download it, and you can then use it as we go through the hands-on exercises in the next part of the tutorial. All right, so with that, let's get started. So of course, we are at MLSys, right? This is all about machine learning and AI. So ML has had like tremendous success across across vision, language, recommendations, and games, right? And the key engine that's been driving the AI revolution is essentially training these models, right? So you kind of have a model, it's typically a neural network. You feed it with a lot of data. In this example, many images. And training the network essentially involves feeding it this training data set, updating its weights to model the underlying function that represents the data set. So broadly, of course, in the context of machine learning, the idea is machine learning algorithms are trying to make decisions or predictions based on the data, right? So you could, like at a high level, like categorize current machine learning algorithms across the following axes. So one is across, what is the purpose or task you're trying to do, right? Whether it's anomaly detection, classification, clustering, reducing dimensionality, and so on. And then, that's the task. And now you're feeding it a lot of data. How do you get feedback from data? Do you do it via labels? That's where supervised learning comes in. Do you have unlabeled data? That's where unsupervised learning comes in. Semi-supervised or reinforcement learning, where you're kind of, getting a reward and trying to take actions based on that. And then based on this, now the actual method you use for the hyperparameter optimization, which could be stochastic gradient descent, you could be using evolutionary algorithms, you could have rule-based, topic-based techniques, and so on. So this is kind of the large overview of machine learning, specifically distributed machine learning. And this resource here actually is it kind of talks about this entire landscape. Our focus will be on supervised learning with stochastic gradient descent, given that that's the most popular for deep neural networks. So within DL training, there are essentially the following phases. You must be all familiar with this, right? So there's kind of the forward pass or the inference phase, where you're computing output activations based on whatever input samples you give and what the weights are for the model. And then two other operations called backward propagation essentially include weight gradient computation and input gradient computation. And ultimately, the aim here is to, again, try and minimize the overall error with respect to the loss function and try to update the model weights to kind of capture what the underlying data is trying to represent. And we're going to use the term training loop here. The training loop will dictate the order in which we issue the basic compute operations and possibly their communication tasks. So a key challenge in deep learning training today is the fact that, training time is increasing. And this is because of several factors. So one is the fact that, DNNs are just becoming larger and larger. DNNs today have billions of parameters, and, going forward, there are models with like hundreds of billions of parameters and have also touched trillion parameters. Training samples are also becoming larger. So as you know, especially if you think about like recommendation models, you're getting a lot more training data as people are using, and clicking on ads, and training samples being larger means, again, training times can go up. And we can't just rely on, our compute to just become more and more efficient, right? Moore's law has ended, or at least is moving forward in slow steps. And it's not keeping up with the rate at which the model complexity is increasing. And many of you might have seen this chart from OpenAI, which kind of shows this exponential 300,000x increase in the compute required, as you went from AlexNet back in 2012 to AlphaGo 0, right, which actually won the game of Go. So large models also means large amounts of communication, right? So so the challenge with large models is that, if you look at, models like GPT-3 or like Transformer 1 trillion, for GPT-3, you would need at least 16, GPUs just to fit the model parameters, right? We're not even talking about the activations and the intermediate states. And if you have a 1 trillion parameter model, then using like the zero optimization, which we'll talk about briefly, you need 128 GPUs just to fit, right? And so this is just to fit the model, right? Again, and if you want like even more performance and parallelization, you will probably require even more number of GPUs or NPUs. So that's kind of where the notion of distributed training comes in, and the notion of deep learning training platforms comes in. So the idea is that, there is a big trend today to build customized platforms for deep learning training, which includes customized chips for training, right? All the way from, of course, NVIDIA's GPUs are a major leader here. And of course, we are at MLSys, you've probably seen talks and, a lot of startups that have chips in this space. And you want to train the scaling across many, many nodes. So systems like, the Google Cloud TPU, like, NVIDIA's DGX boxes, Facebook Xeon, all of these are examples of systems that essentially have these customized accelerators, and then these are scaled. And there's many more, right? So Cerebras CS2, Tesla Dojo, this photo is actually from downstairs. Like if you go to the booth, like Tesla's Dojo is actually on display there. NVIDIA's DGX, scaled with Mellanox sharp switches, Intel's Habana, IBM Blue Connect. The list goes on, right? Almost every company has some system that they have built which is targeting this problem. And so that's kind of where, we come in. We're kind of trying to, talk about all of these systems in an abstract manner and talk about some of the challenges in this space. So what constitutes a deep learning training platform? So this abstract figure captures the major components. So of course you have your classic, endpoint server nodes with the CPUs connected together. But some of the key components that constitute and which are focused purely on the training task is these accelerators or neural processing units. So we'll just use the word NPU to be very generic. This could be GPUs, this could be TPUs, these could be whatever customized accelerators you have. So you have these NPUs. There is a fabric connecting all these NPUs together. This is what we're going to call a scale-up fabric. And there is a scale-out fabric, which is which is connected via the NIC to scale across, like, many racks and nodes. All right, so what are some of the systems challenges with distributed training? So the first is communication, right? This is kind of inevitable in any distributed algorithm. So what does the communication actually depend on, right? So it actually depends on the synchronization scheme you have. I will briefly talk about this, and the parallelism strategy. So both of these will determine the communication that you have. And the question is, well, is communication a problem? It really depends. It depends on whether you can hide it behind the compute. And so if you can actually hide all the communication behind the compute, then you're really compute bound. You're kind of bound by what your accelerators can do. But if you cannot, then it is a problem, and this communication can start showing up and becoming a major problem for training. So how do we determine this, right? That's kind of what we're going to focus on. So to understand, what the exposed communication might be, you really need to understand the entire, co-design stack for building a deep learning training platform. And this stack is something that represents what happens today. So like we've kind of broken it into three major components: a workload layer, a system layer, and a network layer. And within each, there is kind of a set of abstraction layers, right? So we start at the very top with the actual models you want to train. Then you go to the parallelization strategy you use for these models. Then you come down to the communication policy and patterns, some framework level scheduling. Then you get to the actual system layer where you have your actual, NPUs in terms of the compute capabilities and their memory systems, and the communication mechanism. So this is where a lot of communication libraries come in. You may be familiar with NVIDIA's Nickel, which sit in this space, which are trying to, decide how to actually schedule the communication across the NPUs. And then you get to the actual network layer where you have the transport being implemented, the endpoint node design, the fabric design, the fabric topology, and the actual low-level implementation of the network, right? All of these factors come in. So what I'm going to do is walk us through this stack and kind of just give you a glimpse of some of the challenges and some of the opportunities in each space. And of course, the main problem here is that these abstraction layers are great, but we're also to get performance, we're trying to do co-design, right? So there is this classic tussle between too much co-design would mean that we'll actually lose some of these abstraction layers and make things a little too rigid. But having like very rigid abstraction layers will mean that we lose opportunities to optimize. So kind of understanding this stack is useful, whatever level of the stack you typically operate on, to see what opportunities actually exist. So starting, of course, at the very top with DNN models, here we are talking about the actual model we want to train, right? So things like ResNet, if you're interested in vision, if you're interested in NLP, transformers are extremely popular today. And of course, for large cloud vendors, recommendation models like DLRMs are extremely important and popular. And essentially what these models boil down to, of course, you have the model that you're interested in. From a system perspective, this boils down to the specific operators you have in each of these models. So, ResNet would be dominant with conv2D operators, transformers would be dominant with attention operators and fully connected layers, and DLRMs would have fully connected layers and other kind of operators like embeddings. And the parameter sizes, right? So this is the size of the model. As I mentioned, this could be millions to billions to even trillions. So our focus will be kind of going down the stack from here, right? So okay, now that we have a model, the question is, how do you actually parallelize this across all these NPUs? And so essentially the idea is, I have a training task. I have whatever model I have in mind. What is the best way of kind of splitting it across all the available nodes? And there are several ways of splitting it. So one option is to split across the mini batch. This is often known as data parallel. Another approach is to actually split the model weights across the NPUs. This is called model parallel. And some of these terms are often, not very, very precise. So model parallel is also sometimes called tensor parallel. Or you can split across DNN layers and have each NPU be responsible for running different layers. This is called pipeline parallel. And there's a lot of hybrid schemes which have their own custom names in this space. And the parallelization strategy also defines a specific communication pattern across the different nodes. So if we start with data parallel training, the idea is that you're trying to distribute data across multiple nodes and replicate the model across all the nodes, right? So you take the data samples. In this case, I'm going to represent the inputs with, so I'm kind of going to abstract everything as matrix multiplications or gems. So the inputs are going to be represented by MK, the weights by KN, and the output is MN. So the basic idea of data parallel is simply that I'm going to take this MK matrix and split across the rows here. So each of these is data samples, and have some of the samples be at the first NPU, some of them be at the next NPU, while the weights are actually replicated completely at all the NPUs. So each NPU has a full copy of the entire model. So what does it mean from a communication perspective, right? So during the forward pass, each NPU has the full model and it just needs to run inference on a set of data samples. So there's no communication between the NPUs. So it kind of, each NPU operates completely in parallel. So all you do is, compute the output, go to the next layer and so on. And this is where all of your classic techniques for just scheduling onto an accelerator coming, right? And these techniques just flow naturally. What happens during the backward pass, right? So since the data samples are actually split across all the NPUs, they cannot all compute the full weight gradient, right? So they're all going to compute partial weight gradients, and you actually need to communicate this across the NPUs with what's known as an all reduce to actually get the full copy of the model. So this is the communication flow here, where you're going to compute the input gradients and the weight gradients, and the weight gradients will actually be communicated across the NPUs. This communication is non-blocking. You don't actually need to wait for this to complete, because you only need it once you're again doing the forward pass. So you kind of issue a non-blocking communicate and continue moving forward. At the very end, though, you do need to wait for the collectives to finish before you do the forward pass, because you want the full model before you can start. So that was data parallel. The other extreme is what's known as model parallel, or as I said, tensor parallel, which is again with the same abstraction. The idea here is we're going to split the model weight. So we kind of split across, let's say, the columns here. So half of the model weights go to NPU1, half of them go to NPU2. And the data samples actually get replicated across all the nodes. So as I mentioned earlier, this is in some sense inevitable in some large models today, where the model is just so large that you just have to do it. It's not just for performance, but it is something that's just needed to fit the model in memory. So once you do this, now in terms of communication, because each NPU only has part of the model, like during the forward pass itself, it needs to actually do a communication in order to get the full output activations to move on to the next layer. And you actually need to wait for this communication to finish so that you get the full output activations, which become the input activations for the next layer. So this is the blocking communicate during the forward pass. So you compute the output, issue output gradient communication, wait for it to be finished before you go to the next layer. And in the backward pass, now in this case, you communicate the input gradient. So you can all locally compute the weight gradients, but the input gradients need to be communicated. And again, this is a blocking communication, because you need those input gradients before you can actually compute for the next layer going back, right? So again, this is kind of an example, training loop here, where you compute the input gradient, issue the input gradient communication, compute the weight gradient, wait for the input gradient to complete, and then go to the previous layer. Again, this is, as I said, just an example set of operations. You can kind of rearrange this, but the dependencies definitely need to be maintained. So you can already see, intuitively, that model parallel has a lot more communication than data parallel. There are also hybrid parallelism schemes that are used in practice. So here, the idea could be that, let's say you partition all of your NPUs into different groups, and within a group, you may use model parallel, and across the groups, you might use data parallel. And intuitively, the reason to do this might be simply because, let's say, within a group, these NPUs are tightly coupled with some high bandwidth interconnect. So you have a lot more communication in model parallel. So let's try to have this be the model parallel dimension, while across these you have like narrower interconnects. Let's use data parallel. So this is an example. And as I mentioned again, like in hybrid, the communication will, like, you might have to actually communicate output activations, weight gradients, and input gradients depending on how this split happens. Another strategy one could use is pipeline parallel, where you take the model and you kind of allocate each layer to different NPUs. So in this simple example, there's an N layer DNN, and there are N NPUs, and each of them is mapped to that NPU. So from a communication perspective, now you compute the output activations. You have to actually send it to the next NPU. You have to wait for it to receive all of it before it can move on to do its inference stage and so on. And so this would be a blocking communicate, but this communication is just point to point, right? You just forward it to the next NPU. And during the backward pass, you have to again communicate input gradients. And again, since it's input gradients, you actually need to have a blocking communication, wait for it to be computed before you can move on and do your computation. So pipeline parallel is again interesting in the sense that the communication is quite simple. It's just neighbor to neighbor. However, because of all these dependencies, it's hard to actually get full utilization across all the NPUs, right? Because of these dependencies. So then you kind of have to rely on other techniques to enhance utilization. So one thing that's often done is you decompose a mini batch into micro batches and propagate them in a pipeline manner, so that at any point, you might be operating on some layer for a micro batch while some other NPU is operating on a different layer for a micro batch. And just make sure that you get full utilization across all the NPUs. But it is a challenge. Like pipeline bubbles in pipeline parallelism is an open problem today. There's also, of course, the need for more sophisticated schemes. Just simple, data model pipeline parallelism do not cut it, given the fact that models are just becoming larger and larger and more complex. And this chart from, a talk from Cerebras illustrates this, where very, very large models, 1000x requirement for compute in just 2 years, right? And in this case, today, if GPT-3 can be trained on 1024 GPUs, it will take 4 months. Tomorrow, when you have multi-trillion parameter models, you really need more efficient system solutions across the stack. So this is where there's been a lot of interest in, more sophisticated parallelism strategies. So Microsoft Zero is a strategy where the motivation again is that, we can't use just pure data parallel because we can't fit large models. We need to use model parallel, but then computations are too fine-grained. There's large communication overhead. And and in terms of memory, right? Like, it's not just the memory overhead of the model, but you also need a lot of memory overhead for the optimizer state. And so in this example from the Microsoft Zero paper, they kind of show that, model weights are taking, let's say, this much amount of memory. There's a lot more memory being used for, the momentums and the variance and other such hyperparameters. So what Zero proposes is a set of techniques to kind of partition the optimizer state and the gradient state, and basically tries to trade off compute versus memory versus communication. So the idea is, let's try to minimize the amount of memory we need and kind of communicate some of these as on demand. And so without going to a lot of details, kind of, if this is the baseline which required 120 gigabytes, the most optimized version of the Zero optimizer or the Zero strategy essentially just requires about 2 gigabytes. So if you're interested in more details, that paper goes into more details. So this is one example of, a very like handcrafted strategy that is created to optimize for communication and memory overhead. Other such strategies exist, hybrid strategies, again, depending on the complexity of the model. So Meta's DLRM has a very unique characteristic where if you're familiar with the DLRM architecture, it has an embedding layer followed by a sequence of MLP layers, right? And so the embeddings are really, really large. So again, just like, I mentioned for model weights, you cannot fit an entire embedding table into the memory of a single NPU. So you naturally need to do some form of model parallel. So the embeddings are model parallel, while the MLP layers can be operated in a classic data parallel manner. And so now you kind of have a model where, some layers are model parallel, some layers are data parallel. And there's a very interesting communication behavior that happens here where you kind of have, during the forward pass, the output activation being computed. And then you have to actually issue what's known as an all-to-all communication to synchronize here. You have the bottom half of the DLRM MLP layers will also be computing output activations. You have to actually wait for the all-to-all to finish from the model parallel layer before you can then, compute the rest of the output activations. And then during the backward pass, you are computing weight and input gradients as before. The weight gradients are being, sent via an all reduce. And again, once you kind of come to through half of the MLP layers, you have to issue an all-to-all for the embeddings and wait for all of this to finish, right? So this is just, again, trying to show you a glimpse of, depending on the parallelism strategy, the communication behavior can be very, very unique and interesting. And there's more recent examples, right? So Microsoft's Pipe Dream is a pipeline parallelism strategy, as I described earlier. Megatron is a customized strategy that NVIDIA developed, which was targeting, training of some of these transformer models. And again, this is, as I said, a very, very active field. DeepSpeed and Megatron were used to train Megatron Turing NLG. You might have heard of the Google, Palm work, where they also trained this large language model called Palm, again, in some, hand optimized strategy. So again, the basic takeaway being that in this space, right, the parallelization strategy is important, and the right parallelization strategy is also pretty much an open question. And in fact, there's tools like FlexFlow that are available that can actually help you search for interesting parallelization strategies. So moving down the stack, then we look at the actual communication policy. So here, there can be different strategies. So we've kind of tried to classify them based on the synchronization approach and the communication handling. So you could do either what's known as synchronous training or asynchronous training, and within each, you could either rely on a central parameter server or be fully distributed using collectives. So synchronization essentially defines when nodes should exchange data, and this affects convergence time, right? So there has, of course, been interest in exploring asynchronous training, where you don't actually wait, like each NPU can kind of go ahead and you have, you don't actually wait for all NPUs to finish that iteration before moving on to the next one. And there's been trade-offs of, loss in accuracy versus decrease in training time. But we'll focus on synchronous training, which is typically what's used in practice. So you basically wait for all the NPUs, they synchronize and then they move on. So how do you handle communication? And we'll go into a lot more detail of what this communication is in a few slides. But as I mentioned, right, so just to kind of recap, right, depending on the parallelization strategy, there will be communication either in the forward pass or in the backward pass. And so to handle this communication, either you can actually rely on a central parameter server, where the parameter server is responsible for holding the entire model. And the job of each node is simply to kind of communicate, like compute the gradients and then send it to the parameter server to actually perform the updates of the model. And the parameter server will then send the updated model to all the NPUs to go over the next iteration. Of course, naturally, you can see that here, the parameter server as a central entity is the bottleneck. Again, there's been interesting research here where people have looked at distributed parameter servers as well. So again, it's pretty much an open area of research, but the community has moved a lot towards a fully distributed solution using collectives. So here, the idea is that compute nodes talk to each other more directly and update the model through an all-reduced communication pattern. And these collectives are essentially, derived from the notion of, collective communication that has been very popular in frameworks like MPI, right? And we'll talk a little bit more about collective communication in a bit. So whether you exchange output activations or input gradients, this, as I mentioned earlier, again, depends on the parallelization strategy. And it could either be handled purely by collective patterns, or you could break the collective into individual, node-to-node sends and receives. So when do you need collectives? So collectives, again, are needed typically based on the parallelization strategy you have. So if you have a parameter server, you don't really rely on collectives. There's the central entity which is handling everything. But if you have, fully distributed system, then all reduce is used for model updates. And for input gradient and output activations, it again really depends on what the parallelization strategy is. If you're doing purely pipeline parallel, you don't need collective communication because you're just kind of doing, node to node forward. Okay. So we've talked about what we called as the workload layer. So now what we'll do is move down the stack to the system layer, right? So the system layer comprises of the actual NPU, compute, and memory. So as most of you know, right, like gems are actually one of the most dominant operators in deep learning. And this is just some data showing how much like matrix multiplications or individual multiplications and adds dominate when you're training some models. And essentially, gems show up, as I've already shown earlier, in this form, right? So during the forward pass, you're actually multiplying the input and the weight matrix to compute an output matrix. And during the backward pass, again, you're computing the gradients, and these are also essentially matrix multiplications. So it's no surprise that, on the NPU end, there has been a lot of interest in kind of developing enhancements that optimize for these gems, right? So either there are architectures that are really focused on, SIMD units that are the basic building block, or, there are architectures that are both focused on more systolic like units, which are focused on more matrix multiplication. But the key feature you'll see, whether it's, customized accelerators, or if there are, tensor cores in a GPU, or even CPUs today have started putting these, where you have specialized support for gems. And the focus is to let's just try to maximize the number of teraflops we can get in hardware. But there are certain, again, interesting trends from the workload that make some of these things challenging. So workloads, these gems that I talked about, actually tend to be highly irregular, which is non-square, and in many cases, highly sparse, right? Because of explicit pruning, or because you have activation functions like ReLU and like things like dropout. So what that means is, if you kind of take this gem, like whether it's in the forward pass or the backward pass, and you want to actually map it onto your accelerator, you can actually run into utilization challenges. If you have a very nice square gem which maps perfectly to the shape of your underlying systolic array, then you can get 100% utilization, as is shown on the left here. This is simply a classic, weight stationary style accelerator. But if you have irregular gems, then it becomes a lot more challenging to get utilization. And if you have sparsity, naturally you have zeros in your array, and in your matrices, and getting utilization is hard. So on the NPU end, there's been interesting trends towards enhancing utilization to handle irregular gems. One interesting research question is whether you should build, very, very large arrays like the Google TPU has, large 128 plus 128 matmul unit, or should you have several smaller quote unquote tensor cores that are connected via some network, right? So you could basically at an abstract level view the NVIDIA solution as that, like small tensor cores across many, many SMs. Of course, the trade-off is, data reuse versus utilization. You might get better utilization, but you have, reduced the amount of data reuse. You have to write things back and forth to buffers as opposed to just forwarding them over wires. On the sparse end, I think recent trends have been to at least add support for structured sparsity. So NVIDIA's A100 is a classic example, right? 4:2 structured sparsity. And there's also, of course, active research going on in looking at more kinds of structured and even unstructured sparsity support. Another trend on the workload end, which makes things challenging, especially on the training side, is related to operation, to op intensity or arithmetic intensity. So, convolutional layers are great. There's a lot of opportunities to reuse. Filters can be reused across images and images across filters, and there's sliding window behaviors, which basically means that you actually have a lot of opportunities to reuse data on chip. But if you look at things like transformer models, you have some of these, intermediate components like logit and attend, which end up having a lot less reuse, which means that they end up being a lot more memory bound. So this roof line is just trying to show how convolutions typically tend to be, nicely compute bound, but a lot of fully connected layers and attention layers tend to be memory bound. So this is a problem. And again, there's kind of a big trend in accelerators today to enhance memory bandwidth. Of course, if you just look at the trends in the GPUs going from HBM2 to HBM3 with some of the latest GPUs, there's a lot of interest in just adding a lot more memory bandwidth. So what does all of this mean from a training perspective? So what's interesting is if you really make your accelerator highly efficient, you have a very efficient compute array, and you also have a highly efficient memory system, the nice thing is that the compute time per NPU will go down. But the challenge with that is hiding the compute behind, hiding the communication behind compute might become even more challenging, right? So this is some studies we did with our simulator where we kind of saw what would happen if your accelerator became more and more efficient without, anything changing on the actual fabric side. And you can see that, the communication actually becomes much, much worse, right? So you might have cases where, as you scale, your actual performance drops because communication starts dominating. So this is where, with relation to the compute, optimizing the communication is also necessary. So on the system layer, one key piece is the actual communication mechanism you use. So this is where collectives come in. I've already talked about collectives a few times. So this is kind of mathematically how collective communication can be represented. And these are the more, the standard ones typically used in deep learning. So reduce scatter, which basically means that, you're going to reduce these partial gradients and then kind of scatter them across several NPUs. So each NPU gets kind of a full reduced value of part of the gradient. So this is used during input exchange, output exchange due to model parallelism. All gather is kind of effectively like a broadcast where each NPU has, these 4 gradients, and you broadcast it so that everybody has the full copies. All reduce is basically a sum of these two. So you do a reduce, scatter, and an all gather. And all to all is typically where you essentially take all of these gradients. And again, I guess this is not very clearly visible here, but you're essentially, doing an all to all communication to all the NPUs. Now, the interesting thing is this is kind of there is kind of the mathematical requirement of the collective, and there is the actual implementation of that collective. And there can be several ways of implementing a collective. So, for a reduced scatter, you might have ring-based, direct, and so on. And I'll briefly talk about this in the next 2 slides and what that means. So let me start with an example. So let me kind of show you how to do an all reduce, a ring-based all reduce over a physical ring. So you have a set of NPUs that are physically connected by a ring, and we are going to run a ring-based all reduce. Again, like the idea is that and so through this example, we'll show how the all reduce gets executed. So in this example, I have 4 NPUs. So I actually take this chunk of the collective and break it into 4 messages. And remember that, this is, let's say, during the backward pass of a data parallel training phase, where everybody has a part of the gradient, right? And they want to actually reduce this and like get the full gradient. So I break it into 4 messages. And the rule now is node 1 will forward, message 1 to node 2 forwards message 2 to node 3, 3 forwards message 3 to node 4, and 4 forwards 4 to node 1. And you just locally accumulate to that part of the gradient that you have. So in the first step, this is basically what's going to happen. And so this gets accumulated. So in the next step, everybody just does the same thing again. So in this next step, sorry, what has happened? Yeah. So now 1 gets forwarded here, gets added here, 2 gets forwarded here, 3 gets forwarded here, 4 gets forwarded here. And finally, in the next step, 4 gets forwarded here, gets accumulated, and so on. So at this step, like in 3 steps, basically, like in a 4-node ring, I have finished a reduced scatter. What does that mean? Now, at the end of this, each of them has, accumulated this part of the gradient completely, and I've completed a reduced scatter. This was done completely in parallel. There was no contention, right? Every message, there was only 1 message on each link of that ring at any point of time. So it's a very, very efficient way of doing this. And that now you have to do an all gather, which basically means kind of forward this to everybody. So again, on a ring, like, you just keep making copies of these and forwarding it to your neighbors. So again, in 3 steps, you are back here, and all gather is done, which basically means now a full all reduce is done. Now each of these are fully updated gradients, right? So you have the full model state that is updated. And this is again very efficient because this was a ring and this was a ring-based all reduce. Well, what if you had a richer topology? You actually had an all-to-all connectivity between all the NPUs. Then you need not have actually done it in so many steps over a ring. You could have actually done it via what's known as a direct all reduce. So in one step, everybody sends, let's say all of the nodes send their copies of gradient 1 to node 1, and it adds it up. Everybody sends their copies of node to a gradient, the message corresponding to gradient 2 to node 2, and so on. And then this is reduced scatter in one step. And then everybody just does a broadcast, all gather in one step. So this is a direct all reduce. Right? Now, if you, of course, perform a direct all reduce and your underlying topology was a ring, then you can start seeing that there will be contention. So this is something that we'll come back to. And similarly, all-to-all, if you have like an all-to-all connect topology, it's very easy to do an all-to-all. You just basically do this kind of a broadcast. So this is where this notion of topology-aware collectives comes in. So depending on your underlying physical topology, you can actually choose different implementations for the collective. So kind of I showed a ring-based, all reduce and a direct all reduce. There's also something called a halving doubling all reduce, which is very popular if you have a switch-based architecture. And again, the idea being that if you have that underlying topology, a topology where all reduce is very, very efficient. But if not, then it could lead to congestion. So of course, collectives can become more and more sophisticated as you have more and more sophisticated training platform, right? So in the actual topology of your training platform might not just be a single ring or a switch, right? It might be a more hierarchical version. So you might have a torus. Let's say this is similar to what Google has in the cloud TPU, or you might have, let's say some GPUs connected in some dimension, let's say on a package, and then you have all of these connected via a switch. This is, let's say, similar to NVIDIA's DGX2. So here, you have additional challenges. Your bandwidth is more heterogeneous, and you have what are known as multi-phase collectives that you implement. So you actually, so this is an example of doing all reduce in a hierarchical manner. You first do a reduce scatter within the package here, then you do an all reduce across the rows, then you do an all reduce across the columns, then you do another all gather within the package. So at the end, you've done an all reduce. And essentially the idea of this hierarchical thing was that you try to actually have 2 sets of communication within the package, because that's where bandwidth is higher. So there's kind of techniques like this. Similarly, hierarchical all reduce could be done here as well. So as you have more and more dimensions, you can kind of break all reduce into these hierarchies. And within each dimension, you can use a topology-aware collective, right? So here within this dimension, it's a ring. So let's use a ring-based all reduce. Here within this dimension, there is a switch. So let's use, let's say, halving Dublin, right? So all of these strategies exist. Again, like all of these strategies exist. It's not very easy to automate a lot of this. So this is still pretty much an open challenge today. A lot of the collective libraries still typically implement, they'll just do a ring-based all reduce, but they've started adding more and more support for hierarchical all reduces. Then once you've kind of decided the algorithm for like the specific implementation, you still need to kind of schedule all of these onto the underlying topology. And this is where, suppose I have a hierarchical all reduce, you as I mentioned earlier, you kind of do a reduce scatter in the local dimension, then you do an all reduce across the horizontal, which would mean like reduce scatter followed by all gather, and then all gather in the local dimension. Now, one challenge that comes in here is, remember, as you're doing a reduce scatter, as you're doing a reduction, the size of the message keeps going down, right? Because you're kind of accumulating it along the way, which basically means that some challenges you could get into are things like this. And this is something we actually demonstrated in our recent ISCA paper, where suppose, the chunk size is initially 12 megabytes. As you kind of go through a hierarchical all reduce, the size of the message goes down. And then as you do an all gather, of course, it goes back up. But what that means is now you have different size messages traversing these dimensions at different points of time. And so the delay could be quite different. So you can get into scenarios where you have, different delays through different dimensions of your training platform. And so naturally the slowest, stage will end up determining the overall performance and become the rate limiting step, right? And you have idle time. So you have uneven pipeline stages. How do you address this? So this paper that we had, Themis, if you're interested, you can check it out, actually comes up with a greedy scheduling strategy that tries to schedule across all the dimensions in different orders so that it maximizes bandwidth utilization. Okay, so now let's move down the stack even further. Let's come to the actual network stack now, right? So now that we've kind of logically decided and we've decided the schedule, now we need to think about the actual underlying implementation of our network. So we start with the transport layer. Here you really need to, again, there's different options, right? You could either have transport protocols that are purely, implemented in software and software terminated, which are extremely flexible. Or you might, but of course, they're going to be slow, right? You're going to get limited by the CPU. Or you might have things that are purely in hardware, right? So TCP would fall in one end, which is, purely a software-based solution, but naturally, the CPU might become a bottleneck. RDMA is one that relies on hardware. For training, in fact, there's, especially with GPUs, there's been more optimized RDMA implementations like GPU Direct and GPU Direct Async, which try to actually leverage, the GPU memory rather than relying on the CPU memory. But again, these are hardware terminated. These are high performant, but they're not very flexible. So there's also, like interesting research. So this paper, if you're interested, talks about another transport protocol called 1RMA, which actually has some aspects of this still running on the CPU. So the control, like some of the network policies about congestion can still be, flexibly managed from software, while some of the more heavyweight computations are done in hardware. So again, this is a very, very interesting and open space. There's also a lot of interesting questions about the right congestion control protocols to use. If you have, just classic data center workloads, there's been a lot of work on congestion control. But if you're running distributed training, what kind of congestion control matters? So this is a recent paper that we had published. If you're interested, you can check it out. That actually goes into some of these and compares some of the classic congestion control techniques. So overall, I would say that a lot of interesting research questions in this space are around impact on training time and what is the best policy, especially if you have more complex and sophisticated parallelization strategies. So moving down the stack even further. So now let's think about, how do we design the actual endpoint? So here we need to think about the design and connectivity. There's interesting challenges that come in at the endpoint. So, suppose you have, let's say, some GPU at the endpoint, and you have a bunch of like SMs here. Remember that during training, you have the actual compute running, which is the gems, and you have some of these reductions, right? Because of the collectives also running. And they all kind of get scheduled on the same GPU, right? So you have some SMs that are kind of focusing on the compute. Some of them are focusing on the communication. And they're also, so there's sharing the cores, and they're also naturally contending for memory bandwidth, right? So you kind of get into challenges where your NPU is very efficient, but your part of the NPU's compute and memory resources are being used by communication, which makes it very, very challenging to drive the rest of the network. And in fact, this is some data we got from Meta, where as part of this collaboration, we actually measured what would be the slowdown if you had compute and communication running together versus you had communication running on its own. We saw that there was actually tremendous amounts of slowdown in some cases because of this overlap, right? So you ideally want to get overlap, but because of the overlap, you're also adding contention. So then possible solutions here could be to try to offload some of these communication tasks onto or near the fabric. So in this work, we actually tried to develop a specialized endpoint accelerator that was optimized purely for running collectives, so that your compute and memory bandwidth is now available for compute. There's also other approaches. NVIDIA had a very interesting paper in ISCA 2020 where they actually showed how you could optimize the switch architecture to run collectives inside the switch. So trying to optimize for collective support inside the switch or at the endpoint at NICs is again a very, very interesting and open research question today, with a lot of interesting opportunities. All right, moving down the stack even further, okay, now that we have the endpoint nodes, how do you actually connect these nodes together? How do you build optimized topologies? This is an example I showed earlier, where this is just a snapshot of something like a torus topology that is used by the TPUs. There could be other topologies as well. Now, if you have a torus, whether it should be like fully homogeneous or should you have heterogeneous number of components per dimension? All of these are interesting questions, especially because, as I already mentioned, right, as you're running these collectives, the size of the data also changes, right? So there's a lot of interesting interactions between the number of dimensions you have to traverse, which can lead to underutilization, but more dimensions would mean, of course, you might finish things faster. So choosing a topology is pretty much an open question today. You might also have asymmetric topologies, just not by choice, but because of technology limitations, right? You might have, let's say, GPUs connected with NVLinks, which are very high bandwidth, but you can only go so far. And beyond that, you have to use Ethernet, right? Or InfiniBand, which will have lower bandwidth. So how do you kind of design a system and guarantee that you can get efficiency across all of these? And again, here you have knobs you could play around with. You could kind of go up that stack, co-design stack, maybe change the collective algorithm to be multi-phase so that it matches well to the underlying system, right? All of these are very, very interesting questions to look at. And finally, like at the lowest level of the stack, very low level, like thinking about the actual network implementations in terms of buffering, flow control are all interesting questions as well. So this is some experiments we had done where we were trying to compare different kinds of systems. You have a flat topology or you have a hierarchical topology, and you're running either like a single phase all reduce or you're running a hierarchical all reduce. And we were trying to see how all of this affects low level parameters like this, the switch buffer size, right? So if you have these switches and you have buffers, how does the size of the buffer essentially affect overall performance? So again, without going into details, this paper actually is one where we did these experiments for DLRM, and we were trying to study some of the sensitivities to global switch size. Okay, so this is kind of, just to summarize what I've talked about so far, this is the entire co-design stack. All the way from, which we've broken into workload layer, system layer, and network layer, kind of for an ease of analysis. And on the workload layer, we focus on the models, the parallelization, the communication policy, and the framework level scheduling. On the system layer is where we actually focus on the NPU design and the memory system architecture and the communication libraries that will kind of decide what the collective implementations are. And the actual network implementation is where you kind of physically build the network, all the way from some of the software layers like transport to the architecture of the server nodes to their connectivity to low level features like switch sizes and buffer sizes. So how do you actually navigate this codependent design space, right? As I said, because one change at one end could actually have a huge impact somewhere else, right? So how do you decide what the best strategy is? What is the most cost-effective strategy? What gives you the most bang for the buck, right? So this is kind of was our motivation to develop ASTRA-sim. I think when we kind of started this work, we saw that there was not a lot of tools available in this space to do such kind of an exploration, especially for system designers. There's a lot of tools available for ML, developers to kind of work around with model architectures, but for system architects, there were not a lot of opportunities. So we kind of went ahead and developed ASTRA-sim. These are just two of the papers that go into most details of ASTRA-sim, and we plan to kind of release more details as well. So again, so ASTRA-sim actually faithfully models this co-design stack that I mentioned. So it has a workload layer where it essentially implements different kinds of training loops. So remember, I mentioned training loop is the way the compute and communication operations are getting kind of running, right? The order in which they're running. So it supports several parallelization strategies. So natively, we have given training loops for data parallel, model parallel, and hybrid parallel. And it's extensible to more training loops. And we actually have an active development where we also allow you to directly get graph-based inputs from PyTorch, which means you can have any of your sophisticated parallelization strategies that I talked about, and they can go through ASTRA-sim directly. On the system end, again, this is where for the compute and memory, you actually plug in an external simulator, and that's something we'll talk about when we go into details. And for the communication mechanisms, we provide several implementations for these topology-aware collectives like ring-based, tree-based, all-to-all. And we also allow you to run both single-phase and multi-phase collectives. There's a variety of scheduling policies that are already implemented, including, I mentioned, like this work called Themis that tries to optimize the schedule. And again, compute times are fed in via an offline simulator, or you can just feed in real system measurement, right? So compute is really just taken in as an input, as we'll talk about. And the main beauty of ASTRA-sim, and I guess, as I said, a lot of this was motivated by trying to study communication. The main beauty is this network API that actually lets you plug in different network simulators to study communication at various levels of fidelity. So you can play around with topologies, like you might be interested in topology studies, flow control, link, right? Whatever you're interested in, or transport. And so we have plug and play options. There's an analytical model which is provided, which lets you do very, very fast studies. We also have Garnet from Gem 5, which models credit-based flow control and is more detailed and cycle level. There is an analytical model with some congestion support that's in progress. It's which is also available. And we also have leveraged NS3 to study TCP and RDMA in some of these papers. Again, this is also something that's supported, and we will talk about this briefly as well. So what does ASTRA-sim report? It reports end-to-end training time, communication time for each operation, the amount of exposed communication, which is basically telling you like how much of the communication was hidden behind compute, how much of it was exposed, and like more detailed stats such as average message latency per hierarchical collective phase. So this is what ASTRA-sim reports, right? The front end, workload and system layer. And then depending on the network simulator you use, there might be like network specific stats you can get, like bandwidth utilization, communication protocol statistics, network switch buffer usage, and so on. So to summarize what I've talked about so far, large model distributed training is an ongoing and open research area. There's many emerging supercomputing systems that are specifically designed for this problem, right? As I mentioned, so Google's Cloud TPU, like, Meta's Xeon, NVIDIA's DGX boxes, like we mentioned, like Tesla's Dojo, which is on display downstairs in the sponsor room, Cerebras CS2, Intel Habana, IBM Blue Connect. Again, the list goes on, right? Like almost every major vendor has a special platform that they've built for addressing this problem. And co-design of the algorithm and the system actually offers very, very high opportunities for speed up and efficiency. So with that, I will conclude my part of the presentation. So I gave you an introduction to distributed deep learning training. And next, we'll actually have Srinivas Sridharan from Meta, who will kind of give you an industry perspective and talk about some of the challenges for distributed training systems. And just to kind of, for those of you who came in late, this is the agenda we'll follow. After that, we'll have a short break. Then we will kind of, after that, we'll have the actual introduction to ASTRA-sim from Saeed, where he will talk about the details of the simulator. Then after a short break, we'll have some hands-on exercises from William and Taekyung to kind of show you examples of running ASTRA-sim and playing around with various knobs. The website includes the agenda. It also includes, the source and Docker image. So if you want to go ahead and download it, that will be useful, especially once we get to the hands-on phase. I believe the Wi-Fi is somewhat slow, so it will be good to probably download it and keep it before we get to that.